All right, folks, welcome back. Let's get started. This is lecture 6 on cross-modal learning. So just some assignments for the upcoming weeks. So the midterm assignment is due soon. I put up the instructions on Piazza. The two key deadlines are after spring break, April 1st, Tuesday, and the report is going to be due. It's a 6-page report. And on Thursday after spring break, April 3rd, will be the presentations. So for April 3rd, just because there's a lot of team members, a lot of groups, we're going to put class time from 1 to 3 p.m. We're going to be understanding if people have to go at 2, that's technically when the class ends. If you have to go at 2, let us know. So we'll reschedule you for the first hour. If you are scheduled to present in the second half from 2 to 3, we're also flexible if you want to come to class at 1:30, 1:45, and so on. But if you can, try to come to class for the full 1 to 3 p.m., even though we can't mandate that. So let us know your schedule and we'll finalize the list on the order of presentations to be sent out. The requirements for the midterm is that you should have, at least, of course, you should have decided on the idea. You should have decided on what data sets you're going to use, what baseline models are the key things that you're going to be comparing to, and ideally process those data sets and baselines. And some results from running those baseline models and highlighting the main errors that those baseline models make. And then ideally, you would have done some initial progress towards your contributions. So implemented to some extent your ideas and showing that it does, address some of the key errors, key limitations of prior work. Do you have a question? Okay, great. So that is assignment for the midterm. Someone just make sure the door is closed, please. And the reading assignment, this fourth reading assignment is due tomorrow, Wednesday, in preparation for this Thursday's discussion. And this reading assignment is primarily about multimodal interactions. So different ways, different modalities provide information, how they combine with each other, and how do you model that using machine learning models. Two very exciting papers, one really old and one pretty new. Old paper on 10 myths of multimodal interaction, still very relevant today, discussing from a HCI perspective, when you do user studies, do people actually use all the modalities, and how do humans perceive different modalities that they are given? And the second paper, very recent, using mixture of experts and foundation models for multimodal fusion. Great. So midterm assignment due the week after spring break and reading assignment due tomorrow and discussion for Thursday. So in today's lecture, we're going to wrap up our discussion on multimodal learning with this idea of cross-modal learning. We're going to cover the basics and several ways that we can achieve cross-modal learning. And cross-modal learning is super relevant. This is the idea where you are trying to transfer information between modalities, right? There's some task, some modality that you want to get your model to work on. Very often you might have limited data. For example, if you're working with medical data, there's going to be some limitations. If you're collecting real-world sensor data, you're not going to have too much data. How do you transfer larger sources of data towards the tasks that you actually care about? We're going to cover 3 paradigms. Firstly, very quickly, because I'm sure most of you have seen some glimpse of this, I'm going to cover some amount of transfer learning, like latest ways of transferring information through pre-training and transferring it to downstream tasks. We'll then cover this set of methods, which is called co-learning. So co-learning is this idea where you introduce some extra modality during training, either at the input or the output. So you introduce it during training, but once you train the model with it, you discard that second modality. So that during testing, you only take in the modality that you care about. So we call that co-learning, and we'll discuss ways of doing that. And finally, we'll look at ways of model induction, which is the idea that you can induce some behavior across your models, even though you only have black box access to them. It's super relevant given nowadays a lot of these large models only give you black box API access. So first part, transfer via pre-trained models. So in this setting, you often have some large model with large amount of information stored within its parameters, for example, BERT, LLM. And the goal is to transfer that information by adapting it in some way to the modality that you care about, which is probably going to be different from the pre-training distribution. And the goal is to really adapt that model, which we call fine-tuning, for some specific task. So I'm not going to cover too much about LLMs yet. There's a whole lecture dedicated to LLMs and large multimodal models after spring break. But I just want to say that oftentimes you are going to be doing some amount of multitask or transfer learning. And the key definitions of these is, if supervised learning just gives you X data to labels Y, and multimodal supervised learning has X1 and X2 to Y, then multitask learning is the idea where you use X to predict 2 tasks at the same time, and if they share information with each other, then ideally the performance on both tasks improves. Transfer learning is this idea where you take X and you predict Y1, or maybe X prime, so self-supervised pre-training, and you transfer it to some new task Y2. And again, the goal is that this transfer is better than just supervised learning from X to Y2. You have cross-modal learning, which is the extension where you might pre-train on one modality, for example, language, for some language tasks, and you transfer it to X2, for example, to code, which is similar to language, but not exactly language, or to genomic sequences, which is again close to language, but not exactly language. And finally, you have lots of methods that take in X, predict X prime instead of predicting a label Y. So that is usually called self-supervised pre-training, and then you transfer it to some task X to Y. Okay, so this is just quick because I covered this in week 2 when I talked about different ways in which you could collect data and different training paradigms. And most of you have probably seen some notion of multitask or transfer learning, I'm hoping. So today I'm going to cover, at least in the first part, multitask and transfer learning on steroids. So there's this new paradigm of methods where they basically done multitask and transfer learning across many different modalities. So here's a general setup. This is from some of our earlier work. If you look at a lot of these multimodal data sets today, let's say for understanding humans, you might have language, speech, and gestures, and some annotation on human behavior. But then on multimedia data, you have some partial overlap in the modalities, right? You also have image and text, even though the image and text are not exactly the image and text that the person is speaking. And when you go to robotics, you're going to have some sensor data, and some of this sensor data overlaps with medical data. So in medical case, you also have some of these sensory information from ICU, for example. So nowadays, there's been this new generation of methods that doesn't just do multitask and transfer learning within a domain, within a group of modalities, but now they're doing multitask and transfer learning across very, very different input modalities and output domains. So here are some references. Our paper was called IMMT, and there's also this paper called Generalist Agent, which does it more for multimedia, robotics, and several reinforcement learning tasks. Yes?
Paul, can I ask you a question in the previous slide?
Oh, yeah, sure.
So in the transfer learning, so the second column, do we care about the accuracy of Y1 or is there a relationship between the accuracy of Y1 and Y2? So for example, there has to be a high accuracy of Y1 in order to achieve the high accuracy of Y2.
Great question. Usually higher accuracy on Y1 correlates to better transfer performance.
Okay.
That's why, in most of computer vision research, you have a good model pre-trained on ImageNet, and Y1 is ImageNet accuracy, the better it transfers to other things like medical images. Same thing nowadays. That's not mine, right? People want to mute their computers. Nowadays, you have LLM, you pre-train and you measure perplexity, and in general, the models which are better perplexity or better at this, some set of basis tasks, like it's a multitask language understanding. MMLU is a common way of doing Y1. They will transfer better to whatever other tasks that you think about. Of course, there's exceptions. There are scenarios where you really overfit to some tasks, and the more you get better at Y1, the less it transfers. It's also a possibility. Great. So yeah, so nowadays we have methods that really do multitask and transfer learning across very, very different modalities and tasks. And this can be very useful because if you're looking at, for example, some medical tasks or design tasks, even within that domain, you're not going to get a lot of data. So you really have to leverage other domains where you have more data. So nowadays it's increasingly common to see, these methods where even though on the surface, very different input data, you can all serialize them into a sequence, right? You can put language as a sequence of words, speech as a sequence of, sampling rate of, whatever frequencies a person is currently saying. Image can be sequence of pixels. Sensor data can be sequence of time steps. And once you serialize everything, we've seen that transformers are pretty much a very reliable way to learn at a first order approximation the relationships in that modality. So how words interact with other words, how one facial expression interacts with other facial expressions, how one time step in your sensor data interacts with other time steps in your sensor data. So these unimodal transformers are increasingly general, and in fact, you can apply one model with the same parameters for everything. And likewise, multimodal transformers, which learn the pairwise interactions between modalities, are also becoming increasingly general. So they can be used to learn pairwise interactions between words that you're speaking and your facial expressions. They can be used to learn information about demographic information about the patient and other time series ICU information that you're recording from the patient. So the good thing about some of these models is that, first of all, you can see this is massively multitask. It is one model trained on very different subsets of input modalities and for different prediction tasks. And they also show this phenomenon of transfer. So you could transfer by training a model on, for example, 3 tasks with 3 sets of input modalities and transfer it to a 4th one. So let's say you transfer it to a medical case. And then you see there's some overlap. This time series that you see in robotic data and the time series that you see in these medical data. There's some overlap and there's also some new information in this new medical task. And we've shown results where performance consistently improves. This is the performance where you just train on the target task, supervised learning, 67%. And you start training on 1 different task, it gets better. You start pre-training on 2 tasks, even better. 3 gets even better, and so on. And likewise, for some other partition of pre-training and transfer, it gets better with the more modalities and tasks that you pre-train this model on. So we've really seen some of these really, really general multimodal, multitask models. I mean, there's some very key assumptions these models are making, which may be violated in different scenarios. One key assumption is that you can standardize everything as an input sequence. Some data is more appropriate to be seen as sequences, and some data might be less appropriate. You're assuming that the only thing that identifies what modality it is just this one hot embedding. So language would be 1000, video is 01000. It basically is using a one hot embedding to identify what modality it is, and to identify that, for example, video appears here and also video appears there. So it's not really capturing a lot of specific information, and maybe you could do better. It's using one shared multimodal model for everything. And of course, nowadays there's work in basically doing mixture of experts, as you will read in the reading assignment, where maybe you have some experts that do fusion here and some experts that do fusion over here, but there's still some information sharing across your multiple experts. Question?
In the last slide, you mentioned about different tasks on the medical mimic data set.
Yes.
What were those tasks? And the next question I have is, in the case of transfer learning or transfer of modality on different tasks, when you trained on the robotics data set, which was time series, how did evaluation transfer to mimic for medical domain? And just numbers or something?
Yeah, so in this case, these were kind of the 3. There was some multimedia video classification, there was some human behavior videos, there was some robots, which was vision and sensor, and you're trying to transfer it to mimic. And then you would get something like train on 0 means just supervised learning on mimic, and you might train on 1, 2, 3, increasingly more source tasks for transferring to the target task. And I guess for the other question for robotics, it was also one of the tasks that was pre-trained on, but then we tried other combinations. So I guess this was transferring to this humor detection task. So you pre-train on some other videos and some other human behavior, and you transfer to this humor task. I mean, you can look at the paper for some of the exact numbers. Yes, Michelle?
Yeah, so paper set, right? And there were like fusion for different kind of modalities in like using for application. It was like using audio, text, and then image, but they would use the kind of media to first do it with audio and then do it with video and then like image. I was wondering why would it be like text like that?
I think it depends on whether you have all 3 data at the same time. If you have text, video, and audio, and all 3 at the same time, then I'm not sure why they would do that, but one reason could be that sometimes you have text and video data, and separately you have text and audio data. But you don't see all 3 at the same time, so text could be this thing in the middle that you use to define a common support for those 2 data sets.
So I was thinking maybe audio and video audio and the image may be very disparate, so maybe we want like text sense. A little bit more similar to the image modality, and like more similar to audio modality, and then using that instead of
Right,
or quite similar.
maybe. Yeah. I mean, it depends on what the intuition was in the paper. Yeah. You had a question you're saying?
So I think in the previous one, you mentioned there's like video and different kind of data.
Right.
But when you try to transfer to this mimic task, mimic is only like structural data.
Yes.
How these other modalities information could be translated or transferred to the multi-modal model? Multi-modal model.
Yes. So mimic here is time series and tabular, right? That we use the two modalities, and you see evidence of time series in the other ones as well. In fact, so there's time series of robots, and even though some of this audio, video, they're higher dimensional, but in effect, they are still mostly time series. Is it mine? In effect, it is still mostly time series. So right here, to show kind of this method, we basically were able to train one transformer encoder that really works on everything, right? It's able to process language and speech and gesture and video and time series. And the only thing that is different is this identifier. This one hot identifier that identifies what modality is coming from.
How do you identify whether the information is related to the specific task or not?
Well, then the model is, there's a task-specific head that is kind of fine-tuned. So the idea is that these will learn general purpose features, and the task-specific heads will learn the task-specific features.
Is it that easy to do the domain-specific learning?
There can be challenges. Okay, folks, I have to move on, but I mean, there's so much interest, the paper is there, and I also included a bunch of other references. This was kind of as of 2023. We kind of did a survey, and these were all the models that did some amount of transfer between modalities and tasks. So this was perceiver, where it's a general architecture that works for everything, but the colors are different, so they don't actually share the same parameters. You have models that try to standardize image, vision, audio, and you have some models that try to, for example, do language, vision, audio, transfer with each other. So as of 2023, this was the landscape of multimodal, multitask, and transfer learning. Great. Okay. So in the second part, the first part was mostly multitask and transfer learning as a way of leveraging information from different data sets. In the second part, we're going to look at this phenomenon called co-learning. So in co-learning, you have this modality that you care about, and we're going to introduce some extra modality B during training, only available during training, to learn a better representation. You can think of it as a better co-learned representation that enriches the information in A, the modality that you care about. General paradigm, the key idea is that B is only introduced during training as an auxiliary information, and during testing, this is the only branch that is activated. It's still just using A to predict the label. That's why it's fair to compare it with just supervised learning models using A to predict the label. Okay? There's three ways of doing co-learning that I'll briefly cover. They all have kind of pros and cons. Sometimes they work, sometimes they don't work. The first way of doing it is fusion. So you have A and B. You learn a fused representation. If you recall from fusion, you have this setting where you have two modalities and you learn one joint representation combining them together. You learn a fusion representation, and during test time, you put input zeros. You zero out modality B. So see what that looks like for learning via fusion. Let's say you have two things. During training, you have A and B, XA and XB, and you would define a fusion model between XA and XB to predict the label Y. During testing, you would zero out the input to modality B. Either replace it by zeros or replace it with the average value for that modality. So now during testing, it's still only using A, passing it to the fusion model to predict Y. Okay? And what is the baseline? Baseline in this case is unimodal learning, right? You use A to predict the label during training, you train your model weights, and during testing, you just use A to predict Y. Okay? So it's fair comparison because during testing, when you're using the model, is only just always taking a modality A, say language. It's just like training. I train this fusion model between language and vision when I do co-learning. So only text is used at test time, and there's been performance that shows consistent improvements using this co-learning, this paradigm as compared to directly visible supervised learning. So this was our work. The context was A was language, and B was nonverbal information. So nonverbal facial expressions and vocal expressions helps you learn about language than directly learning about language in a supervised setting. Here's some other evidence. This is actually a very seminal paper called Multimodal Learning with Deep Boltzmann Machines from 2014. In this setting, it was also a fusion model. It's just that a fusion model they used with a deep Boltzmann machine. Maybe all of you are too young to know what that is, but it's an earlier class of generative models. Think of it as precursor to these variational autoencoders. But the same idea remains. You take A, B, you learn a joint diffuse representation, joint probability distribution, and you see this multimodal deviant generated text was outperforming these image-only models. And this generated text is basically their way of saying during testing, only image is given, right? So the first four are image supervised learning. You could use LDA, SVM, and these are deep Boltzmann networks, deep Boltzmann machines, deep belief networks, deep Boltzmann machines. These are just image-based supervised learning methods. We call these. And this is a setting where you train a joint multimodal model using image and text. But during testing, you remove the text and ask the model to infer it itself, right? So everything's fair comparison. Everything's only given image during testing. Here's another cool example. Another very seminal paper, 2011, called multimodal deep learning. In this setting, they also trained this shared representation. So again, joint representation between, in this case, audio and video. But what they would do is that they would train it using audio, and then they would try to do testing in video. And they showed that this was actually competitive with video training and video testing supervised learning. And it's super cool because the task they tested on was this McGurk effect task. You recall the person had the sound, the ba ba ba, ga ga ga, and they had their lips moving, which is a video. And the goal here was to take in the audio and video to recognize what phoneme the person was saying. So this is also some cool evidence of co-learning via fusion. So key idea, during training, you have more modalities. You learn some shared joint representation. And even though during testing, something might be missing, fill in with zeros, or the average because it's missing, it still outperforms doing supervised learning only with the present modality. All right, so interesting way of just boosting performance, right? If you know that you want to do video-based prediction, you can always do video supervised learning. But sometimes learning this joint representation with video and more things could be better. So that's co-learning via fusion. A different paradigm, but also within this co-learning space, is co-learning via alignment. So the same setup remains. A is what you care about. Normally, you might do supervised learning using A, but now you have this extra B during training. And you learn a better enriched representation. Instead of doing fusion, where A and B come in and you learn one representation, you can do alignment, where you have A and B, and you are learning this representation space where A and B are separate, but aligned through some similarity function, right? We saw a lot about multimodal alignment 2 weeks ago. So some very early evidence, again, this is a very seminal paper from 2013, zero-shot learning through cross-modal transfer. So in this case, it was kind of like early version of CLIP, right? So you had lower resolution images from CFAR10, some car, some dog, and you have word embeddings, right? Word to vec, word embeddings. And basically you will learn this aligned representation space where maybe the word embedding for auto is over here. And nearby in these crosses, you have image embeddings that were embedded into this space. And you have this similarity function. So the word embedding nearby has all image representations of cars. And likewise, word embedding for horse, and these images of horses embedded, and for dog, and likewise for horse. So you would train a model with this alignment function, the thing that we discussed 2 weeks ago, where you had data, you define encoders into separate representations, and define some similarity function, usually cosine similarity or L2 distance. And you bring these corresponding pairs together, and you will push apart the incorrect pairs. So that's during training. You learn this aligned representation space. And during testing, let's say you have this new image, this very low resolution image of cat that comes in. And normally if you try to do image classification and you've never seen cat before, you just will not be able to predict it, right? You don't have that dimension in the softmax that predicts cat. So you will never predict cat. But the good thing is of this aligned representation space is that you can project the image into that representation space, and you can find the nearest neighbor word embedding, right? And this word embedding space has structure. Cat is very close to dog, but not exactly the same as dog, and can be further away from horse, right? So you can just find the nearest neighbor word embedding, and therefore you will be able to do zero-shot prediction and say this image should be labeled as cat. Okay. So again, evidence of co-learning where during training you have words and images, and you're doing this alignment in representation space. But during testing, you only have images, right? You only just need an image, and you're trying to look up the nearest word embedding, and so that enables zero-shot image classification. And nowadays, of course, we have scaled up versions of this. We have flip-like models. We have all these other models where during testing or during training, you have text and images. You do this aligned representation space. But once you learn this aligned space, you can transfer it to many downstream tasks, including those that only use a single modality. So transfer the image encoder to ImageNet, to retrieval, and to other image classification tasks. So training using image and text, you do alignment, and downstream inference, you only use prediction tasks on one of the modalities. Better than supervised learning directly in the target modality. Here's some more cool evidence. Some people call this cross-modal prediction. So this is a robotics example where you have these robot arms that was manipulating different objects, and you had vision and touch. So vision will be from cameras like that, and touch would essentially be whatever force the robot feels while manipulating that object. And this red and green essentially shows data in which it was actually paired together. So this vision corresponds to that touch, and red shows incorrect touch patterns. And this is vice versa. This is the touch, the force that was sensed. This shows the positive visual pair, and this shows a negative, incorrect visual demonstration of the robot. And again, over here, what they show was that you could train this model using vision and touch, and you would learn this aligned space that either classifies it as true, as coming from the same demonstration, or fake, in which it would be the wrong demonstration. And that learned good representations that would then transfer to vision only and force only tasks. So again, examples of co-learning for alignment. You have two modalities. During training, you learn some aligned representation between them, and this aligned representation is useful for tasks in only one of the two modalities during testing. Okay, last type of co-learning. So you see co-learning via fusion and alignment. Both of those have an extra modality B in the input space. This third example uses this extra modality B in the output space. So during training, you would train an AKA. You will learn some features that would predict modality B as a prediction objective. And the hope is that by predicting this additional modality B, this auxiliary task, you learn better representations that could be used for eventually just test time prediction using A. Okay, so we call this co-learning via translation. So three ways, fusion when B comes in, or alignment when B comes in, or translating B is on the output. So some examples. We had done some work where, again, this was data where you had language that the person was speaking and visual expressions the person was making while they were speaking something. And the goal is to understand sentiment and other behaviors. So normally when you do fusion, you need both modalities at test time, right? So if something is missing, then you're in trouble. So one other way of doing it is to essentially do this translation where you take in language you predict some representation, and the representation should be able to decode the person's visual expressions, essentially hallucinating what the person might have been expressing while saying those words. And this representation, even though it's kind of a translated representation, it should still be multimodal in nature, right? Because it encodes language, but it kind of just keeps a part of language that is the most relevant towards predicting the visual information. Somebody celebrating. Okay? So it should still be a multimodal representation. And therefore, you can use that representation for sentiment prediction. And during test time, what happens is you would have trained this model. You would take in language, you will go through the forward pass to encode the representation, and you will just pass it through the classifier head to predict sentiment. And you will not predict the visual anymore because you don't have to predict the visual during testing. So you do cross-modal translation during training, you need both language and the corresponding vision. But during testing, you just take in the language, predict the representation, and then predict the label. So we also showed here that these bimodal translations further improve performance. So you could first use language to predict vision and go through a representation. And then you will use what you predicted in the visual space to reconstruct the original language. So this idea of cycle consistency, right? So if you use language and you're terrible at predicting vision and it's all like random noise, then you'll be even worse at reconstructing the original sentence. Forward and backward translations. But it's still co-learning because once you've done this during training, all you need to do is take in language, predict the feature, and decode the label during testing. So during test time, you still have language only. And we show that this outperforms just doing supervised learning only on language. This idea of predicting the vision. Several other examples. These multiple papers argue that co-learning is useful for compositionality. So over here, there are some computer vision tasks that require the model to be super fine-grained and predict where things are and how many things are on top or above or the same color as something else. It can get really, really hard questions. And if you just did supervised learning on these, sometimes the model might not capture those fine-grained details. So what these folks found is that you can do auxiliary training, which you can discard at test time, exactly the message of co-learning, where you take in the vision and you predict the language, right? Because in this case, language really captures this compositional structure of what is above and behind something else. So during training, you would take in the image, you would learn representations that can predict the description, very compositional sentences, and then you throw it away during testing and just predict images, predict the image during testing. All right. More examples. This was a paper I enjoy very much on extending masked language modeling. So everyone's probably seen this, right? You have a sentence, you mask out certain tokens, and you train a model to reconstruct the missing tokens. And this allows you to learn representations that essentially take into account the context, using the neighboring words that were present as context to predict the missing tokens. So you get humans learn language by listening and speaking. Now, what these folks found is that in addition to doing masked language modeling, you could also do masked visual token classification. So Vulkan classification, where Vulkan stands for visual tokens. So while encoding these texts, you will predict what humans look like, you will predict what language looks like, however abstract that might be, predict what listening, speaking all look like in vision. Which is very natural. I think a lot of people argue that this is how humans learn because we hear people speak and we imagine visually what happens. We see vision and we imagine the sounds. A lot of people who do AI inspired by psychology argue for this approach. Again, the evidence is that during training, you use text to predict the missing text tokens and also to predict the images. Once you learn that representation, it just takes in text during testing, right? And that has been shown to improve upon just language-based language modeling. Final example that I want to show is this idea of dense and sparse supervision. So over here, what these folks are doing is that they're trying to use breathing data to assess Parkinson's. Apparently there's some correlation between how you breathe and whether you might have early symptoms of Parkinson's disease. So you can collect 10 hours of breathing, nocturnal breathing, so when the patient is sleeping, and you have 10 hours of data. The only thing that you can predict is likelihood of Parkinson's, which is just one bit of information, right? One number. And you can see why that would be very difficult, because you have a lot of data. You can learn the encoder, but it's a lot of data. You just have one very small number to predict as training signal. It's very, very sparse training signal. So all this is just a breathing encoder, Parkinson's disease predictor, classifier, severity predictor. All this just predicts one number. So one natural thing that you can do is to try to use another modality to give more supervision than just this one number of whether they have Parkinson's or not. So one thing you can do is you could predict the EEG at the same time. So EEG is brainwave, I think, brainwave stuff. So you can take this breathing, which is 10 hours worth of data when the person was sleeping. And while they're sleeping, you also collect, for example, their brainwave activities. And so therefore, this is also 10 hours. And this gives you really rich supervision because you have this task of using 10 hours to predict 10 hours while also predicting your one number of Parkinson's or not Parkinson's. So this, they named it auxiliary task for multitask learning. But it's also an example of how you can do co-learning via translating from one modality to the other. Right, so that's what it looks like. You take in your breathing data and you predict EEG activity throughout the night. And again, they show that the better you're able to predict EEG data, the better you could also learn representations to predict early onsets of Parkinson's. Yes.
So, I mean, the idea is very kind of interesting because I guess the difference in data scale or size. So is there like just empirically that works, I guess, or is there like also some law, between different scales and relationship of how well this kind of learning framework works?
You're talking about theoretical guarantees, then it will really depend on the assumptions that you make, right? I'm sure people have set up simple toy classification problems, made some assumptions about the two modalities and their mutual information, made some assumptions about where the task information is, and you could prove some stuff. My intuition is that when you're doing this translation, you're essentially learning what is common between the two modalities, right? You take in, sleep data is so much information, and a part of it overlaps with EEG. So like a Venn diagram is learning that overlap. That's what you get by translating. And it so happens that Parkinson's indicators are also perfectly within that overlap. Then you're basically good, right? If otherwise, you might not be good. I was going to discuss some of these intuitions later, but I have the same intuition for these other methods based on fusion and alignment, because everything that these are doing is just introducing more objectives to capture the information that is common between the two modalities. So the assumption is, yes, the task should also be within that common region. Yeah.
In the common region is actually going to be the task that we thought of. Because maybe with like breathing, maybe stress or something as an auxiliary task. And maybe how do you figure out like whether that actually helps with the Parkinson's?
I mean, many different factors that you hypothesize something. In this case, they probably talked to doctors. They did many rounds of trial and error. So there's no really set question to that. Probably a mix of intuition and trial and error. And same thing, why did they use EEG and not something else? I mean, there's many other things you could think about. Probably some trial and error. And the same goes for a lot of these other examples that I've shown. I mean, speaking of trial and error, I want to show also failure cases. So not always this works. So, there's a line of works. Basically, when you see a paper that says, does something help? ? And probably the answer is doesn't help. because otherwise they would say results are great. So here, if folks remember BERT with very early large-scale language pre-training, and when BERT came out, it crushed a lot of NLP tasks. And then we have things like video BERT and visual BERT, which was learning joint representations of language and vision or video. And in fact, people found that these video BERT and visual BERT was better at NLP tasks as well, right? Not just vision language tasks, but also NLP tasks. So positive evidence of co-learning. And these folks show that in fact, for many tasks, there is negative evidence. So when you start with BERT, you get 90% for semantic role labeling. This is some word classification task. And once you start training BERT to predict the video and vice versa, it actually gets worse. In fact, in some scenarios, it can become much worse. Over here, 76 to 65. So 10% drop when you start training it with video and vision. And so these are some examples of the NLP tasks that they found the performance to drop. And you might think, these are NLP, you don't need vision and video. But then they also show some examples of tasks like common sense question answering, common sense reasoning, where it might seem that vision is very important, right? I think this data set includes tasks like, if I give you a question, how you should remove gloss from furniture, and the answer is that you could rub it with a steel wool or cotton ball. Probably makes sense that if a model has seen videos of people doing that or instructional videos, that it should do better. But no, you can start training these video BERT and visual BERT, and performance improves a little bit, but sometimes it can drop quite a bit. So there's limits to co-learning. Not always works. Great. So in this last part, I'm going to discuss model induction. So again, extensions of transfer and multitask learning. But in this case, we're going to mostly keep to APIs, where you might not have access to the internals of the model, because as you saw in the co-learning, you probably usually had to train fusion or alignment or translation. So you needed to have internal access to the model. We're going to cover also methods that don't require internal access. So two key algorithms I will cover in the rest of the lecture. We're going to start with single modality case. This is called self-training, and we'll use that as warm-up to go into two modality case and discuss this algorithm called co-training, one of the most famous multimodal, multi-view algorithms that has ever been invented. So self-training is an algorithm, in fact, it's actually very relevant to these LLM nowadays, right? The intuition is that you might have some label data, XL labeled, and I'm just using 1 to show the first modality. So label data with Y and some unlabeled data without Y. So in this self-training setting, you would usually iterate between training a classifier on your label data, okay, call it F1, and you essentially use the classifier to then go and label more unlabeled data that you have, but you don't have the label. And usually there's some procedure to labeling this unlabeled data. Often you find the most confident examples first, and you label them, so you call it pseudo-labeling in some sense, and then you add it back to your label set and retrain your classifier on the union of the original label data and the new examples that you have labeled. And you repeat this multiple times until you've labeled all the unlabeled data, and you've subsequently trained your model on all the data. You repeat until you have no more. And then during testing, you just output whatever your classifier predicts. So unsurprisingly, probably there's a lot of evidence of this working nowadays, data augmentation, pseudo-labeling in both LLMs and other machine learning models. Question?
How do you know what is the most confident example? Like, do you just validations?
Great question. I mean, a lot of proxy heuristics. Usually, you can make inference on a classifier on some data point. It will give you some softmax distribution. So you won't know the actual label, you don't know the answer, but you can look at whether the softmax distribution is like this, which is very certain on the output maximum label, or like this, which is less certain. So that's one way of measuring confidence. You don't have, because it's unlabeled data. If you have ground truth, you just train label supervised learning. I mean, visually, to see how it works, let's assume this is your labeled examples. And that's a classifier that you originally trained. And let's assume that these are all new unlabeled examples. Red is one class, blue is the other class. And right now it's getting kind of this red triangle is kind of on the dot, on the fence, kind of incorrect, very uncertain. And so you would essentially pseudo-label your data, starting with the ones that are the most confident. In this case, confidence is how far away it is from the decision boundary. Right, so these are very confident. This is very confident. These two are not confident. Okay? You label that using your own classifier. Sometimes people call it pseudo-labeling. You re-add it to your labeled data sets and retrain your classifier. So you see how that will impact the shape of the classifier. It'll kind of move over here because there's more points over here than on this side. So this classifier becomes kind of shifted that way, and now it gets both of those correct, right? The ones that it was previously uncertain about. So that's self-training. Extension in two views, co-training. This is one of the very seminal papers, 1998, still very heavily used today. Basically an extension of self-training to two views. Again, we're going to assume that you have some two views of the data, x1 and x2, your classic multimodal setup. You have two classifiers, and you have some labeled data x1, x2, and y, and some unlabeled data just x1 and x2. But critically, it has to be paired up. Okay? And there's some key assumptions that you have to make where this idea, again, the two modalities are redundant. So there's a common information between them is what is critical for the task. Can't be too much unique or synergistic fusion information. And how this co-training algorithm works, very similar to self-training, is that you will have some, again, labeled data, x1, x2, y. You have some unlabeled data, x1, x2, probably a lot more unlabeled data. You will train one classifier on each, right? You train F1 on x1 to y, and you train F2 on x2 to y. So now you have two classifiers that you start with. So you take one of the classifiers, and you will label the most confident examples in that same modality, and then assign that as a label to the other modalities classifier. Right? So in this case, F1, it labels the most confident data in the first modality, and it assigns that as the y of F1 to x1 to the second modalities classifier. And you train the second modalities classifier on what the first modality had assigned as a label. And then vice versa, you would use F2 to label the most confident samples, the second modality, and assign that as label for the first classifier. And the first classifier will train on the data that has been labeled by the opposite classifier. And you basically iterate back and forth. And therefore, you see it's important that the labeled data is paired, because if I use the first modality to label the unconfident examples here, I'm essentially assigning it to the one that is corresponding. So this is called co-training, same as self-training, but with this two-view flavor. And you repeat until everything has been labeled. And during testing, you would, given some data, you could just use either classifier, or you could ensemble, pick the majority vote between both of the classifiers. My question?
The pairs is a very strict requirement.
Yes, I'm sure there's been work to really relax that assumption.
Oh, that's going also question. So it's in, I guess in the vanilla case, it's,
Yeah, you need paired. So my data, my first classifier is labeling what is confident in X1's unlabeled data space, and I'm going to look for the corresponding X2 and assign that label for this X2, and vice versa. So this, even though 1998, very, very seminal work, nowadays used very much. Here's an example of activity recognition, and you have video data, which video gives you RGB, frame-by-frame images, and you also have these optical flows, which tells you kind of continuous time motion, the person doing those activities. And again, there's, intuitively, there's several examples where RGB is more important to detect the activity from static images, but then some other examples like golf, where movement is very important, probably more important than the static images. So co-training has been shown to work very well here, because you can essentially train an RGB classifier and label flow data. And you can train a flow classifier to help you label RGB data, and they learn back and forth from each other. More examples in language models. So here was an example where the two views are GPT-3 and BERT, 2022 paper, so probably still using BERT. And again, these views are very much complementary. GPT-3, of course, bigger, better at completing text. BERT smaller, and at that time better at classifying different things using its representations. So again, they did co-training where GPT-3 model will label some data that you could use to train BERT, and BERT model will label some data that you can use to train GPT-3. And nowadays, even more examples of basically assuming that these models are APIs. Multiple LLMs are APIs. You don't want to modify the internals so much, or you cannot even modify the internals, but you still have this flavor of multiple agents, debating or conveying information to each other or labeling data with each other. So many examples. I think this co-training work really inspired a lot of this. All right, great. So to wrap up, cross-modal learning is this idea of transferring information between modalities, usually from things that are higher resource, more data, to things that have low resource, less data, but that you actually care about. And we saw 3 examples of transfer and multitask learning. We saw examples of co-learning where extra data is introduced during training, either as input or output. And also this idea of inducing behavior between models, but you're keeping only black box API access. And several tips, decide on secondary modalities, decide on whether you want to do auxiliary input or output, and decide on whether you are preferring to modify model internals or you have more black box access. And again, all of these methods assume that there is some redundancy. So transfer means you can also only keep what is common to both, or is fusion, alignment, or translation, which just exploits the common information. And for model induction, there's also this assumption that both views give you something similar. I've not really seen how you can do cross-modal learning with going beyond this assumption of redundancy. Great. So wrap up, so far in the class, we've seen these foundations of AI. We basically wrapped up intro to multimodal, multimodal connections and alignment, interactions and fusion, and today was cross-modal learning. Next week, there's no class for the spring break, and then when we come back, we'll discuss large models, modern generative AI, reasoning, interactive agents, and all the latest stuff. All right, and just a reminder, again, please make sure you're working on the midterm assignments. That's going to be due the week after spring break, report and presentation, and reading assignments due tomorrow and discussion on Thursday. All right, thanks everyone.